Hi dear, this is Kamal Sarma. I am going to discuss more about bending moment and shear force diagram on today's lecture. And let us start. This is a beam, consider simply supported beam. And simply supported means it has got this side is your hinge or pin supported, the other side is roller supported. This is simply supported beam. This type of beam is very common in bridge structure. I told you earlier, one of the lectures, probably video number 2, that why we make it roller supported, because we allow it to freely move in this direction. This is because L alpha T factor, delta T factor. This is your elongation. Elongation of the beam. So if you restrain this one, the bridge will buckle, the beams will buckle and bridge will collapse. So that is the reason we need to have the arrangement like that, roller support, so that it can freely move this direction. And today's lecture will be discussing about concentrated load. So from here to here, total distance is 15 meter, or if you follow foot or feet in American system, you can consider is 15 feet. The unit doesn't matter, okay? And and I'll be using the metric value for many of my followers have the metric system, SI system. But some of the people here in the United States, they follow the the imperial American system, foot pound. Okay, so I'll be putting the same dimension but with different units. Okay, so then you will understand fully. So let us see, we have two different points here and here. We have, say, this is your 10 kilonewton, and here we have a load of 15 kilonewton. Or if you follow the American system, consider this is 10 kilopound and it is 15 kilopound. But one thing you must be sure, that these two units are not same. 10 kilonewton equal to 2.25 kip. This is the conversion. And 1 meter equal to 3 feet, 3.4 inch. So they are not same, but I'm using the same number with different units, so you understand why I am doing it, because my calculation will be the same, only the units will be different. Okay, so now, we have two concentrated load. There's a point load 10 kilonewton or 10 kip and 15 kilonewton or 15 kip, and distance is 15 meter or 15 feet. And from here to here it is 5, from here to here it is 5, from here to here it is 5. 5 meter or 5 feet, it doesn't matter. Unit doesn't matter. The value matters. Yeah. So now, I have 5, 5, 5. Now first of all, I would like to say, how do you come across the concentrated load? How do you have it? in buildings and in bridges, both you might have concentrated load. Assume in a bridge, because I'm a bridge engineer, that's why I prefer to have a bridge example. So in bridges, sometimes, not nowadays, but in earlier bridges, they used to have two big plate girders. Then that is two big plate girders. And there are some cross frames, not cross frames, cross floor beam. They are connected. These are floor beams. They are also I section. They are also I section. Okay. And they are connected with some. They are connected with some floor. The stringers. The stringers are smaller beams. And on top, say stringers are like this. On top, they have got a deck. So what happens, the load from deck or the slab, you can concrete deck, that is carried by the stringers. The stringers pass on to the floor beam, and floor beam collected all the loads from the deck and put it here as concentrated load. If you see the plan of this, something like this, these are the two main girders, and the cross frames like that. No, cross beams, sorry, or floor beams. The cross beam or floor beam, and there are stringers there. This is the Fleming plan. So what happens? The load from that, suppose this is the spacing between the floor beams. From here to here, whatever the deck load, that will be carried by the stringers. These stringers. The stringer is connected to the floor beam. Okay? And the floor beam eventually transfer the load at these 2 points. These loads are concentrated load. So whatever value of whole thing from here to here, this is the tributary area. So this area, to total load, will come to here and so come to there. The total area will go there as concentrated load because this load is carried by the stringers. Stringers transfer the load to the cross beam or floor beam. The floor beam eventually transfer the load to the girder as a point load or concentrated load. That is how you have the concentrated load. The building, the same thing. If you have a building with, we have two beams there, two major beam, heavy beam. They are connected by some smaller beams. So there's a deck over here. The load coming to this beam will transfer here as a concentrated load. So if you draw the plan, suppose you have got this deck. There's no column there. The columns are here under the beam. So you have got a big beam here, big beam there. There's a beams here also. But there's another beam there. but there's no column underneath. What it will do, the load from this part will transfer. This is the tributary areas. Okay, so columns will be under this. Here is the column, here is the column, here is the column, here is the column. This is the main beam and this is the secondary beam. Okay, the secondary beam will collect this tributary area load. Half will go there, half will go there as concentrated load, point load. This is how you have got a point load. We'll be considering the combination of all the loads later on to find out how it behaves on the bending moment and shear force diagram. Let us take this case. We are single out the concentrated load 10 kilonewton and 15 kilonewton, or 10 kip or 15 kip. Now we have to draw the bending moment and shear force diagram. What will you do? What will you do? We will be doing, this is there will be horizontal reactions there also. We can ignore this reaction because all the loads are downward. So VB, your VA equal to 0, and here is your VA, and this one we straight away consider is RA. There is no other reaction to reaction A or reaction B. Sorry, this is the B. The point is B, this is A, so it is RB. Now first of all, we would like to find out the RAB and VA. This VA. HA is automatically 0. There is no horizontal force there, though this will be 0. Now take moment about this point. Okay, so all the forces on the left hand side, whatever is there, this and this, from this point. So 10 times, so we have a convention. If you have got a clockwise moment, we have a convention, right? That this is positive, this is negative. If we consider from right, the anti-clockwise moment is positive, clockwise moments are negative. So RB, take moment about this point, RB into 15, okay, that is equal to, these are negative, so they are in opposite sides of the equation. So 10 times of this distance, 5, 10 times 5, then plus, this will cause a clockwise moment, this will also cause a clockwise moment. You are pushing it. If you consider something like this, if you have this point, this load is coming down like this, right? You try to push it like this. This is a clockwise. It moves in a clockwise direction. Similarly, this one, the clockwise. This one is anti-clockwise. So anti-clockwise is positive and clockwise is negative. So it is on the other side of the equation. So we have 15 times 10. So this is 50 plus 150, right? Got it? So together they are 200. So RB equal to 200 divided by 15. Okay? So it will be, we cut out, you take 5 common, so 40 on 3. So this will be 13.33. This is kilonewton or kip. This reaction RB equal to 13.33 kilonewton or kip. Got it? Let me check the equation. 50 plus 150, 200 divided by 15. I take 5 common. So 3 divide 200 by 40, 40 divided by 3 is 13.33. Alright? So, now find out what is the PV, particle reaction at B. So, this will be, now you see we have this reaction we calculated by this equation, sigma moment or summation of moment equal to 0 at this point. Okay? The equilibrium equation. Now we will be taking help of summation of vertical force equal to 0. That is another equilibrium equation. There are 3 equilibrium equations. One is summation of moment is 0, summation of vertical force is 0, summation of horizontal force is 0. So horizontal force is automatic. There is no horizontal force, the reaction is 0. The vertical force equal to 0, that means your this VA plus RB equal to 10 plus 15. So, but RB already we know. So, VA plus 13.33 equal to 25. So, what is VA? VA will be 25 minus 13.33, that will be your 6741 and 21, 11.67. Right? So this value VV is VA equal to 11.67. Now I'll be showing you one trick. When you see the heavier load closer to the reactions, you automatically know the reaction here will be, reaction value will be bigger than other side. Here you see 10 kilonewton is closer to A, but 15 kilonewton is closer to B. So heavier load is closer to B. Somehow if you find in calculation, some error in calculation, you find that this is smaller but this is bigger, then you should recalculate it. You have to find out why it is so. You might have made some mistake. So always when the heavier load is there, closer to a support, the more reaction that will occur in that particular reaction, particular point. So as because the 15 kilonewton is bigger, you have got a reaction is 13.33, and the smaller force is closer to this is away from that, we have little less reaction value. Okay, this is either kilonewton or kip. Now let us draw the bending moment and shear force diagram. Now this is the baseline. Okay. Now we have a convention. In my last lecture I was telling you, this is our convention. Upward, if you consider from left to right, upward is positive, downward is negative. So it is the positive convention. So this is positive, this is negative. This is positive, this is negative. If you go from left to right, If you come from right to left, just reverse. If you consider this value from right to left, it will be like this. This is positive, this is negative. If you are calculating the value from right to left, vertical upward is positive, vertical downward is negative. If you calculate the value from left to right, this direction, your vertical upward is positive, vertical downward is negative. That is the shear force convention. Always remember from which side you are calculating the values. If you are calculating from left to right, this is positive, upward positive, downward negative. Consider from right to left, your upward positive, downward negative. This is the convention for shear force. Okay. Now upward. Now we draw 11 points. Here. From here to here, there is no force there. Suddenly it goes up at this point. So how much it is? How much it goes up? 11.67. Okay. So there is no force in between. So this value remains constant. So it remains constant. Then at this point, just left of this point, it is still there, 11.67. As soon as it arrives at this point, suddenly the 10 kilonewton comes down. So 10, that means this value here will be 11.67 positive, negative 10, it will be 1.67. Still positive. Okay. So we have it is coming down by 10, but still positive. This value your 1.67. Then there is no force in between. So it will go like this, constant. So here suddenly 15 comes in, downward, negative. So here what will happen? This point, just left of this point, just left at this point, still 1.67 is valid. As soon as it reaches this point, just right, this 15 comes in. So it was 1.67 positive minus, because our downward, we are considering from right to left, sorry, left to right, downward, negative. So minus 15. So this will be how much? 15. It is 33. 14 minus 1 is 13.33. So, but it is negative. You have to, this is the baseline. Above it is positive, below it is negative. So this is the baseline. Above it is positive, below it is negative. So suddenly this comes down like this, and this value is 11 point, so this value is 13.33. Okay. So now there is no force in between. So this controls all the way there. Then you come, you are facing this 13.33 going up. Okay. So this force will, this is positive because we are considering from left to right. This is still positive. So it is going up, taking it to the positive direction, but 13.33, negative 13.33 plus 13.33. So it will be 0. That is, it is merged with the baseline. So this is negative. This is positive. This part is negative. This is your shear force diagram. Okay. Now, suppose you are thinking of doing it from right side. See what happens. In the right side, we have the convention. This is positive. Sorry. It is positive. Okay? And this is negative. You can draw it similar way. This is negative and this is positive. This is the negative direction. I made a mistake in my finding the reactions, the convention. This is just opposite of that. If you consider from left to right, right to left, the vertical upward is negative. So if you consider from right to left, this is the convention. Vertical upward is negative, downward is positive. This is positive, this is negative. So this is your baseline. This is 13.33 going down, upward is negative, 13.33. From here to here it remains constant. Then downward is positive, it is going up 15. So this is positive, then again it will be added, it is 1.67. Okay, so it is going constant, nothing there. Up here the 10 adds up, going up, so it is the 11.67 from here to here, straight coming here. Upward, we are considering for upward is negative, so this upward force is negative, this is coming down. So this is your shear force diagram. No matter which way you calculate, this is the convention. Upward force, if you considering from right to left, upward is negative, downward is positive. If you consider from left to right, upward is positive, downward is negative. Always remember that. Just opposite. See, it is upward extreme, this is upward, other side is negative. This is downward negative, this is downward positive. Same. Okay. Now this is the shear force. Now let us draw the bending moment. We need to have this bending moment diagram because this is the connection between bending moment and shear force. I will show you. One thing always you remember, when the bending shear force changes from sign from positive to negative, this point is the point of maximum moment. Always it is true. Where the shear force changes its sign from positive to negative, at this point you will see that moment is here maximum. It is. Now another thing you will observe, if the shear force is constant, the bending moment is linear, and when the shear force is linear, bending moment is parabolic. Okay, we'll discuss that later when we have got the linear condition for shear force. Now see what is the values. This is the baseline. Now we have a convention for bending moment and shear force. This is positive. If you consider right side, left side, if it is moment is this way, or the moment at other side like way, it will form like a cup. it is forming like a cup. Okay. So this is a positive moment. Suppose if you have a moment like this, that means it is bending like that, just like an umbrella. This is a hugging moment. It is negative. So what happens? Take this case. This is your load. This force is causing a moment like that. That means clockwise. So your moment here at this point, obviously it is 0, it is free end. So it is starting at 0. At this point, what is your moment? It is 11.67 times 5. 11.67.5. 11.6 times 5. So this value is 11.67 times 5, 58.35. So you have a moment here 58.35. There is no other force at this point. So it is this constant. So our moment here will be linear. Okay. Now, what is the moment there? Now this on the left side we have got the two forces, kilo 10 and 11.7. So moment here will be 11.67 because that will be causing a clockwise moment like this, clockwise moment, and this one 10 kip is acting like this, anti-clockwise moment. So it is 11.67 times, from here to here distance is 10 minus 10 times of 5. This is the value. So what is this will be? It is 116.7 minus 50. That will be your 66.7 positive. So this value will be 66.7. There is no force in between. It is there is no, this shear force is constant here to here. From here to here, shear force is constant. So this is a linear. And this value here will be 66.7. Still all are positive. And you don't need to calculate that moment here is 0, is straight to a join this one. It will be linear because it is constant. So this is your bending moment diagram for two unequal loads at two different places. Okay. So this is 66.7, this is 58.35. So this is your bending moment diagram. And this is your shear force diagram. This is how you draw. But one thing you see, where this is the shear force changes its sign from positive to negative, your moment is maximum. Here it is 66.7. Okay? Do you get it? So this is how it works. Now let us do another quick example. So you understand how to calculate the bending moment and shear force diagram for two concentrated load acting. Similarly, if you have a tree, you can do the same way. Procedure is same. But when the shear force changes its sign from positive to negative, that will be your maximum always. Remember that. If you do not find that, you made a mistake somewhere. Suppose these two forces are equal, both 10 and 10. Both are 10. So one thing always remember, if the load is equal and position is symmetric, okay, see here it is 5 from this end, from here it is 5 and this end. You don't need to take moment to find out the reaction. Automatically 10 will go there, 10 will go there. You can do that. You can do the moment about one point from one side, from other point you take the moment, you find out. This is the wastage of time. If you see that load is equal, the distance from each support is equal, straight away you can say that the 10 will go here, the reaction here will be 10, and reaction here will also be 10. Because it's symmetric. This will go there, equally divided. Now, what is the shear force? Vertically upward, 10. This is your baseline. This is the convention, positive, this is positive. If you are considering from left to right, this is positive, this is negative, downward negative. So this is 10, come there, this is negative, 10, this is 10, keep, okay, kilonewton or keep, either way. At this point, the shear force is there. From here to here, nothing. So it will remain blank, nothing is there. Then suddenly at this point, the 10 will come down because it is vertical negative, downward. 10 keep or 10 kilonewton or 10 keep. Then from here to here, no load is there, it goes there like this, and this RB is going up and they are equal, it merges with the 0 baseline. This is your negative 10 10, this is negative, this is positive. This is your shear force diagram. Okay, now how the bending moment will look like? Bending moment, this is your baseline. What is the bending moment? Because it is simply supported, here it is 0 bending moment. Our convention is, this is our convention. Or if you consider clockwise is positive. Anti-clockwise on the right hand side is negative, or left hand side is negative. Anti-clockwise on this way, if it bends like a cup, it is positive. This whole thing will bend like a cup. So this is all moment will be positive. So now let us see how much it is. From here it is 10 times 5, 50. This is linear, this is constant. So our shear force is linear. Sorry, I apologize, I misspoken. Our shear force is constant, our bending moment is linear. Okay, this value is 50. 10 times 5, 50. This is 50. Now what happens here? There is no load, so it balances out here. There is no load here, no shear force, 0. But the bending moment is not 0. Whatever bending moment there, it will be bending moment there. That is what I say, the when shear force is 0, the bending moment is constant. It will be constant like that. So here also it is all throughout it is 50. Then RB times 5 is 50. If you consider from right, this is also right hand side you are considering. anti-clockwise, it is positive. So this will be like this. So this part, this bending moment is constant, 50. And this part, because the shear force is constant, bending moment is linear. Same is here. So this is how it look like if the forces are equal. It is easy to calculate because if it is symmetric, same amount of values in both is a constant load, then you straight away find the VA is equal to one of the load, the RAV equal to another load. So they are equally divided. So this is the bending moment diagram for two concentrated load of equal amount and symmetrically placed. So I want to finish today. Don't like to solve many more problems, but if you have any question, I'll be spending about 3-4 videos more than that. I'll discuss about all different conditions or all different cases for the bending moment diagram in simple beam. Simple beam means simply supported and cantilever. Both, why they are simple? Because they are determinate structure. You can find out the reactions. So all these cases, possible cases, I will discuss. Then you understand how to draw a bending moment and shear force diagram in classroom or at exam. So I'll be making it thorough with you. You will never make a mistake in the bending moment and shear force diagram drawing. I assure you. If you follow, it is a simple rule you should follow. When the shear force is constant, bending moment is linear. No shear force, bending moment is constant. Like that. If the loads are equal and symmetrically placed, the reactions are, it saves your time in exam hall, especially if it is an objective type of question, you have limited time. This helps you to solve the problem quick. And when you see that the shear force changes its sign, in the other case, you know that, there the bending moment will be maximum. Suppose sometimes in the objective type of question, you ask, suppose a question like this. So it is 15. 15. This is 10. Just ask what is the maximum moment of this. What is the maximum moment and maximum shear of this beam? Straight away you find out what is RB and RA. At least RB, because it is closer. You know this is the load is closer. Then you find out the RB. Find out this multiply by distance. RB times, so there is no load. So that is your maximum moment. Because this is the shear force will be maximum. Shear force will change its sign at this point, possibly. So you have got that time, you have got similar like something like that. So shear force changes its sign from positive to negative. So that is the point where the moment will be maximum. So RB times of 15, RB times of this distance is 5, that will give you the moment there, maximum moment. It will be something like, it will be like that if it is 15. Likewise. So you should if you know the bending moment shear force thoroughly, it will be very easy to solve the problems. So this is all for today. Okay, we'll be discussing more problems on bending moment and shear force diagram next few videos. Then we'll move to stresses. So good to see you and have a good day. Thank you very much.